let's get to the topic of my dissertation, which is the low complexity iterative receiver for IBM systems. And two questions: why IBM and why MIMO? So if we look at the current, communication standards, most of them are, I would say, almost all of them are IBM based, except a few, like DVB, terrestrial, handheld, and second generation DVB, and the first generation H. And if we look at the MIMO standards, the LTE, LTE Advanced, WiMAX and the second generation of H. And why IBM? That is because you need you can design a simple receiver because you do not need a honking equalizer. Generally, equalizer takes around 80% of the area of a receiver if you use a single carrier receiver. Whereas for IBM, it is much lesser. That is the primary attraction. And why MIMO? I did it. The question is, so traditionally it's been as you use a simple equalizer, and what happens now is the world is getting more and more mobile. So if we have the channel that is mobile or the transmitter receiver that is moving, then this simple equalization scheme will not work very well. What happens is when there is mobility, that will cause Doppler spread in the received signal, and that will cause orthogonality loss of the received subcarriers, and that will cause intercarrier interference, and that will cause high bit rate receiver. So we need a bit more sophisticated technique at the receiver, sophisticated equalizer for better bit rate performance. That is for the case of SISO, true for MIMO as well, but for MIMO, even if the system is static, you have co-antenna interference that need to be taken care of. So our idea here is to come up with a low complexity, high performance iterative detection scheme that can combat both IC and CAR. And as we saw, ICA is due to mobility and co-antenna interference is due to multiple antennas. Now, before we delve into our scheme, we'll just see very briefly, what is available today. And more details about that is given in the thesis. We'll just cite a few examples. The traditional non-iterative schemes, which is the DFE and MMS equalization, it is originally from when the time when IBM got popular was in the late 90s, and during those days, people were extending the MMSE and DFE equalization schemes to IBM, and so that's been the traditional ones, and they have low performance compared to the iterative schemes that we are going to see soon. Please tell me, when I was I'm sure there will be. Now, the non-iterative schemes and the other schemes are the iterative schemes, and there are kind of broadly speaking, there are two sets of iterative schemes. One is, I would call it the ad hoc iterative schemes, like these, where whatever is coming from the received symbol is going through a slicer, and ICA cancellation is done at the time domain, and the slicer in the middle is causing will bring down the error as you keep iterating, and this is an example of such class of schemes, iterative schemes. Whereas the major ones, which is nowadays very popular, is the turbo equalization based schemes, where you leverage on the coding gain of the channel decoder, coding gain of the code that you use, and that is the best performer among all the three we've seen. And yeah, more on the literature is on the available literature is in different chapters of the thesis. Now let's zoom in a bit more on the turbo equalization. So let's look at the history of the turbo equalization very briefly. So originally the idea was introduced soon after turbo codes were invented. It was in the 2000s that there was a class of people from DR18 where they introduced the idea of turbo equalization, and there they use they consider the channel as a rate 1 encoder. So it's like you have the channel as a rate 1 encoder, and you have the decoder. That's another. You have an encoder and decoder. So you have two decoders, one on the channel and one on the trellis decoder, whichever your PCJ or whatever. So these two work together as a serial concatenated scheme, and that was so it has exponential complexity, and that was the original idea proposed. Now that complexity was not acceptable for the for practical implementation, so people have been thinking further on. So instead of this, how can we replace the rate 1 encoder idea of the channel into something else? And then came the MMSC linear filter idea. I mean, they instead of this idea, they replace the channel with an equalizer. I mean, the receiver, and so we get an MMSC estimate of the symbols, and it has been done iteratively, and you will see the details soon. So the complexity from exponential came down to cubic because, again, we will see in the coming slides, because of a matrix inversion involved. And then in subsequent papers, they came with ideas to how to bring down the complexity from cubic to quadratic, and further down to linear, and that's from Iris T. In one of the ideas came from. Yeah. And then the key reason, as we said, is because the matrix inversion. Now, what we did is we took it to the next step. In fact, mine was an extension of the work that Iris was doing, and she was working for single carrier systems to deliver turbo equalization scheme. So we took it to the next level, and how can we avoid the matrix inversion altogether? That's the question. So here are the we have our work described in these papers. Now, so this is what we are going to discuss today now. We first talk about the scheme that we have proposed, and then we extend that to MIMO. And so detection is only part of the receiver, and the other part is the channel estimation. So we come out with a channel estimation scheme, a simple channel estimation. The thrust here is simplicity, something that is implementable in a commercial receiver. And then once we look at these, we will get to the error analysis and see. We are making some approximations, and we need to validate that, and that is what is done in the error analysis. Before we get into the details of our algorithm, let's just look at the iterative receiver general structure of that. So we have the information bits that is getting convolutionally encoded. Could be other encoding schemes as well. Then that goes into interleaved, and that all these interleaved coded bits are getting mapped onto symbols, and a few of them, n of them, let me call it, that is the size of the FFT, are grouped together and getting interleaved. That's optionally here. And then it goes through an IFFT, this is the standard OFDM transmitter. And then that is getting prepended with the cyclic prefix. And in the baseband, that's the story. But in the passband, you upsample it, you pass it through a root-raised cosine filter and upsample it, and then modulate it and send it across the channel. And in our case, we are talking about the mobile case. It goes through a time-varying channel and gets added with the AWG in the system. And whatever is coming, the received signal, you just do the reverse operations thereof. Remove the cyclic prefix and group them and do the FFT and do the interleaving. And you make an estimate of the symbol that was transmitted, and then compute the log likelihood ratios. We'll see that soon. And that gets into a MAP decoder, such as BCJR or soft JB decoder. And that gives you another set of LLRs, which are a refined version of the input. And that gets mapped onto an expected value, the the expected value of the transmitter symbol and the variance thereof. I mean, we convert to that. And these two are the inputs. The mean and the variance of the input symbol and the observation vector are being used in the turbo equalizer. T is turbo equalizer, and you make a estimate. And this process keeps going on. We repeat this process to get the refined estimates of x, and that's being used. And so eventually, after sufficient convergence, you get you do a hard slicing of the LLRs and get the symbols out, the bits out. Now, let's look at the system model. So we have the transmit symbols, the passband and the baseband, and we are trying to model the receive signal RSXT, the system matrix in the time domain, and that will be a circle and sort of. We'll come to that in a second. Times the transmit symbol plus the AWG in the system, and that is the receive symbol. And if you look at this, it has got a circle and sort of nature. Had the channel been totally static, this would have been a circle matrix, and that is by virtue of the cycle prefix of the OFDM system. Whereas in our case, as you see, channel coefficients are varying, and because of that, it is kind of, I call it circle and like, but it's not actually circle and. If these coefficients are same, then it would have been circle and, which is the case in a static system. So we get R, we model R, and
so what does circular like mean?
I
mean, it means just simply because it means if the channel were static, then it would be circular.
That's right. Yeah. If the channel was static, these numbers would have been same.
Right.
And if that is the case, then this row will be a rotated version of this, right. Shifted version of that. So then it is the real static. And the reason why I've been stressing on static is when you do an FFT on a circular matrix, then you get a diagonal matrix. And that is primarily the reason for the simplicity of the OFDM receiver. Now here, that is not the case. These are slightly varying. They are slightly different. These coefficients, they won't be differing much. And we'll see the effect of that soon.
So the first index is the time index, right? That's what you're saying.
The first is the time index, and second is the channel tag index.
But these are diagonally dominant when you do the FFT.
That's right.
So that's kind of what I was asking.
Mm-hmm.
Like you have some notion of a condition that it's close to circular, rather than just being any old thing.
That's the name.
Close to circular,
yeah,
as opposed to being just any old.
Right.
I guess what Roy is saying is you should emphasize that every row is maybe some update of the previous row.
Right.
In the sense that in time the things coefficients change slowly.
Yes, that's correct. So it's yes. I mean, it's not. If they were same, then they would have been same. But they like what you said. Yeah, they will be slowly. The difference between this and this will be only minuscule.
So any theorem in linear algebra that finds the circular matrix that's closest to any matrix like that. Find the circular matrix that's closest to a circular-like matrix according to some closeness criteria.
Well, I mean, I just use the term very loosely. Circular.
No, but are you aware of any?
No, I'm not. No.
There are other such results for other types of matrices, like Techlitz matrices. There are theorems, but not for circular.
Okay.
So you know that there's circular.
No, I don't know.
Oh, you don't.
Yeah, we're asking.
He just said he hasn't resolved. There are.
But what you should observe is that if there was no time change, this would also be tuples. So maybe some theory from the tuples closeness would be applied. So in addition to the fact that it will be circular, there will also be tuples. You say tuples. You say tuples.
Yeah, probably right. So the eigenvector will be just like the class for the transport matrix, and then the eigeny will be just on the back of the wall.
And yeah, but when you do the FFT of this, the simplest you can get is the diagonal elements along the, non-zero elements along the diagonal, which is the property in the cyclic matrix. Now, yeah, we are getting to that now. So we know what R is, the receipt symbol in the time domain. So we get the receipt symbol in the so-called frequency domain, and you get Y is FFT of the received symbol, that is Hx plus W, you get that. And H, we are going to see how the structure of the H zone as we, when it is static and when it is time varying. Yes, and W, the noise, is the FFT of the received of the AWGN that got into the system, and that will be, because it's a unitary transform, you have the same values. Before we get into the structure of H and all, we just look at we look into a few definitions. So this we saw this. So we have this turbo equalizer estimation and soft demapper that gets you the LLRs, and then you have a soft decoder that gets you a refined log likelihood ratios, and then you get the expected value of the mean and variance of the transfer symbols. Now, what is LLR, log likelihood ratio? That is it's the log of the probability of the bit being equal to 0 to that of 1, and that talks about the confidence that and the confidence on the bit it being equal to 0 or 1. Now we have this two terms that we are bringing in, the posteriori and the extrinsic. So the way I look at this decoder is it's kind of an LLR transformer, log likelihood ratio transformer. So you feed in some input log likelihood ratio, and you get a refined LLR at the output. Now, this total LLR that is coming out of this, I call it the posteriori, and the difference, kind of the gain, is called the extrinsic. And and we use extrinsic in our calculations for turbo equalization for the mean values. Now, let's introduce all the rest of the. This is block I want to introduce, and this is where we have been. We have our contribution on. So we shall introduce the rest of the blocks, and then we'll get to our scheme. So this CJR, in a nutshell, it maximizes this, and soft demapper computes the LLRs from the symbol estimates, and soft mapper does the reverse, gets the symbol mean and variance from the LLR values that comes out of the CJR. So this is the picture of the complete receiver. So we have the receive symbol Y, and that goes through successive. This is our scheme. These red ones are the new designs. So successive interference canceller, which is what we are going to talk soon about, and then that gets into an LLR computer, and then we talk about the channel estimation as well. Let us look at the property of this H, the circular and like matrix. So as we discussed, for static channels, H is a diagonal matrix. Then for time varying and frequency selective channels, H is a sparse matrix with significant coefficients concentrated around the main diagonal. Meaning, when you have Doppler, when you have mobility, you have Doppler, and so this is the Doppler frequency, and this L is a measure of the Doppler spread. FD is the Doppler frequency, TS is the sampling time, and N is the number of symbols in an IBM symbol. So, as any of these goes up, the Doppler spread, the measure of Doppler spread L goes up, and if you look at this H, if it were static, it would have been diagonal. When there is Doppler spread, these coefficients, the orthogonal elements on either side, it starts getting spread. still it's a sparse matrix, but now you have coefficients maybe not as high as the main diagonal coefficients spread across, and the spreadness increases as L increases, which is as the Doppler spread increases.
To answer Professor Panita's question, you might sort of think, what's the closest diagonal matrix to these banded ones? Because I think like frequency domain and time domain distance should be equivalent. Because if you have a circular matrix corresponds to a diagonal matrix. So instead of looking at differences between circular matrices, you can look at difference from whatever matrix you have to a diagonal matrix. Is that clear?
Whatever matrix in the frequency domain that we have.
Yes. So what's the closest diagonal matrix to that band matrix? In terms of
You cannot find a diagonal banded circle.
closest, not you cannot find the same. Closest. Let's say L2 norm.
Okay. Okay. That ought to be the.
Probably it's just the diagonal elements, I would expect. So you might be working with the closest circular matrix. In fact, I don't know. I'm just guessing.
The transformation is unique, right? So it ought to be that, right?
Yes, transformation is unique. That's for sure.
Right. So.
But the question is, which circular matrix is closest to your matrix, right? That was the question.
Right, and the circular matrix, there is a unique circular matrix that is for this matrix, and that ought to be the thing that comes in our system, right?
I think there's more like for the static channels. So the channel is static. So you have your channel matrix and topology matrix. So every row they are constant. So it's a topology matrix. And in that case, you have your eigenvector as like a Fourier transform, and then you have a diagonal matrix as your eigenvalues.
Yeah.
And then for the time varying channels, that will be not the case. So you have time variation in the time domain, which means you have a little bit spread in your frequency domain. So that's why when you have that time variation, which is denoted by your Doppler, so that it's kind of like a reflecting in that L term, which you try to capture the main energy, like the bandwidth of the time variation in the frequency domain. That's how you end up with this like nice structure.
Yeah, that's always clear. But the question that was posed, which if you have a matrix which was not circulant,
Yeah.
to find a matrix that is circulant but closest to that matrix.
Yeah.
If you convert that problem to the frequency domain, then you get a question from a banded matrix, which is which diagonal matrix is the closest.
Right. I think like there are also researchers who also research how construct a window in the time domain to apply to it, so that when you look at it, they look at like you apply a window in the time domain, and then transform the whole channel matrix from time domain into the frequency domain, and then you look at the energy contained in your band structure versus the energy spread out of that structure, and then you can maximize the energy which is contained in this like a less banded structure versus the energy leaking out, which we kind of like try to, which we neglect those energies, and then you can maximize that one. So that's kind of like what you are talking about, like optimizing L2 law, like maximize the energy contained in.
What you're saying is designing a window, right? Also.
Also, you can apply a window. If you don't apply a window, I mean, you can apply a window. If you don't apply a window, probably there's little energy leaking out of it. But in any way, this algorithm can work. Either you apply it or you do not.
Yeah. I agree. You'll do better with the window for sure.
Yeah, you can.
Moving on. So what is ICA? We've been hearing that a lot. So the energy in the bleeding the energy that is getting bleeding into the adjacent subcarriers, that is basically the ICA. To formulate it mathematically, that is the this term And so this is the desired signal HK, XK plus WK is YK. Whereas when you have a banded structure like this, you have these two terms correcting the desired symbol, and that is the ICR. And this is kind of it is kind of IS in the single carrier systems. You have the ISI symbol interference. This is an equivalent of that in the frequency domain.
But in this case, you only have adjacent subcarriers interfering. You don't have enough spread where you could have, collisions between 2 or 3 off to the side.
No, because these that is the beauty of this. This is a sparse matrix. So along here you can neglect them.
Does that depend on L, right?
It depends on L.
So you're making some mild conditions.
Well, the value of L, if you want a spread as high as this, we are now talking about a Doppler that is very, very hard.
Right, so it's out of the bounds of the
Right. Right.
I think his approach applies to any L.
Yeah.
But I think, like in the examples that he chooses, the L is not too large. In fact, he'll discuss the fact that sometimes, relative to some other schemes, larger L is beneficial.
Okay.
Right. Yeah, we'll see that.
Okay.
And even at plane speeds, we are now. If we
You
talk
should give the slide with examples.
Yeah, we'll just wait for that.
Done future.
Okay. Oh, there it
This
is.
one.
Yes. Exactly. Yes. Yeah. So this is an example. So. So we are now considering a DVB-T transmission, and in say France, and suppose we consider a DVB-T system either inside a plane or that is taking off from the Paris airport. Now we are talking about an L that is just 5.
But L is 2, right? So the total spread is 5.
Right. Yeah. D is 5. Yes. Now L is 2. So this is kind of the high side of L. So now, if you talk about a rocket, it may be L, maybe D, may be 3, L may be 3. But so in generally in all the practical cases, we are talking about small L be 1, generally 1, 2, or 3 at the most. 2. I mean, I can't think of a case where L is 3. So because that the matrix becomes now we see this matrix is sparse, beyond the. Beyond this 2 off-diagonal terms. And now, when we talk about train speeds or car speeds, we are talking normally of L being 1. And so this is the most encountered scenario. So you generally count 1 off-diagonal element, and that will be it could be significant, but beyond 1 off-diagonal element, the coefficients are very insignificant.
Just very quick. If L is less than 1,
the L is the floor, the ceiling
the
of
ceiling, but if you evaluate the number inside the ceiling,
sorry.
there,
What is it that you
at the
can
top, yeah, that from there.
Right.
If you ignore the ceiling,
Uh-huh.
the number inside, like the
Could be very near to 0. Yeah, I mean, if
Less
the
than
Doppler is very low, okay, that's an
Then you
interesting
ignore it.
case. If the Doppler is very low, then what is being done in practice right now is you just ignore it. You just ignore the because the off-diagonal elements will be so low that even if you discard them, your performance is not affected much. So yeah.
it seems like many practical cases fall in that range.
Exactly. Right.
Well, but I think one should observe that maybe one could increase N or TS.
Right.
Or you can argue that many designs were designed for this reason, to make it L small. If you allow for technology to make L large, then maybe you can pack more carriers, or you could.
Talking about that, and maybe you can elaborate a little bit more on that. Say the large-sized OFDM systems like DVB-T2, the second generation DVB, we are talking about 32K FFT. So there the N is so high, and TS being so 9 some 7 over 64 microseconds or whatever. So this term could be high. So even with a low Doppler there, now you can have a high L. So that is one example. Now, the Doppler frequencies depend on the bandwidth and the carrier frequency of transmission and the velocity of the surroundings. So now we are talking about 802.11 BA who are in the 2.4 megahertz region, whereas when we move to N and G AC, then we are not, and even G, it is 5 gigahertz speed frequency, carrier frequency. So and now people are talking about 60 gigahertz transmission. So at those transmission frequencies, we are even with small movements, FD could be significant. So right. Those are some. But in the current existing scenarios, when generally N is 256. Now if we talk about 802.11 series, we are talking N being equal to not 256 or 128 or 64. And so in these cases, what is available today, they generally ignore those off-diagonal coefficients and off-diagonal elements and keep going as if it is a single main tab, single tab equalizer. Now we just have a glimpse of the news, the successive interference cancellation. So we saw that the matrix is sparse for a practical value of L, and there what we do is we just suppose we are trying to find the estimate of. So if we look at this matrix, if we look at YK, that is, we have the ICIs from these terms and these terms. So when we look at this matrix, these rows, these terms will be contributing to the ICI whereas this, if you look at vertically, then it is as if it is giving you a diversity, because you have xk, one single symbol being transmitted, and that is getting into multiple observations here. So that is kind of a diversity case. So we call it Doppler spread diversity, and so you have xk that is getting one transmit symbol is getting you are having multiple observations for the same transmitted vector if you look along this. So the idea here is somehow if you can get rid of these terms, the interfering terms, we'll see how, and take a slice like this of the matrix, then you're talking about a diversity scale. And that is primarily what we want to cache upon.
So the diversity scheme, of course, would be better if those boxes in those, they're very different. But if they're very similar, right? Because then the gain comes down. How do you tackle that?
These coefficients, the channel tabs are the channel tabs are independent. That's you have NH multipath. So these coefficients are not exactly, but they are not highly correlated between. Oh, well, besides this, we have you have the diagonal elements, you have these off-diagonal elements, and these elements are generally different from each other. So
I think the question is, can I rephrase it? You start off by saying that these various perturbations among the rows are very small.
Right.
And then you're going to have this diversity that exists, perhaps, to exploit that. But I believe that the point is there's not very much variation among those sample sets to create an opportunity for great gain in diversity exploitation. So we'd expect to see minimal performance improvement.
Okay.
I think that's the question posed as a statement here.
Okay. We'll see the gains soon, but yeah, that is the diversity. I mean, that is the maximum you can get. I mean, whatever coefficients are coming there, that is the best you can get out of the system.
Great.
And one more thing you can say is once you have higher L, bigger L, these terms get bigger. So you kind of gain more diversity as the Doppler goes up, and we will be seeing when we look at the results, we will be seeing that. So actually, since we are encashing on the diversity, we need the higher the L, the better our scheme ought to be.
But when the coefficients get smaller, if you go away from the center.
That is true, right? And as the Doppler frequency goes down, even then the coefficient values goes down. So this scheme is not will become inferior when you have kind of static channel scenarios, or when we move more towards the static channel case. Because if it is just static channel, you have only single element, you have no diversity at all. So it works like a single data equalization scheme.
And also for the static channel, if you have a fading at one particular diagonal element, then there's no way you can recover it unless you have the coding applied on it, so that you can choose what coding it to recover the signal that you're transmitting on that beam. So here it's kind of the same, that you try to also do the iteration, the decoding and the estimation, so that you can achieve coding gain to help your estimation as well.
What was the hampering you? Was the additive noise you mentioned? I mean, you have only one sample point. You have a single tap issue. What's the big problem?
So when you have when you only have single tap on the diagonal, one tap with totally in the fading, so that energy on
oh, so fading.
Fading will be an
Yes,
issue
and that's
because the path energy is low.
Right. Okay, so make sure I understood that.
Yeah.
I think what I was trying to gather from you is that my feel is that what's also important is the interleavers.
Symbol interleaver.
Yeah.
Right, and that's what we discussed a few times, right? And interleavers are the ones that bring in gain because they introduce independent channels over the carriers.
Yeah, I missed that point there. Yeah, you have a symbol interleaver that could randomize these. That could add on to the diversity. I mean, because having the interleaver there could help further on the diversity.
So your interleaver was kind of glossed over. What is the overriding assumption for your interleaver structure here? What is it?
We are going to see that. The interleaver. So it's coming. Yeah, we look at it when we look at the results. I'll show the interleaver structure there. So what did we see? Yeah, so we just we just discussed this. So you know the coefficients that are far away from the diagonal, and then we do this. This is a significant thing. Like as the log likelihood ratios get more and more accurate, the conditional variance that we saw in the previous slides tends to 0, and the conditional mean tends to the symbol value. So let's believe that for a second, and we will look at the result. When we look at the results, we will see the effects of all this. So if we assume this, then we can use these mean values to compute the IC and remove it as we discussed. And with the diversity, like okay, in the previous slide, as we saw. So we are trying to get the slice. So these terms are causing the ICI. So if we using the mean values that we get from the decoder, the mapper in the reverse path, you compute the ICIs and subtract it off, so that you get this vertical slice like this. So that is how we remove the ICI using the symbol mean values. And then whatever is coming, that Y tilde, which is the ICI removed signal, and that is used. From that you can compute the LLRs easily and do a map decoder. You can compute the LLRs easily. We discussed all these points. And this, I make the statement now, and we'll look at the results. This term is small and decreasing upon multiple iterations, the error. Yes, so this is just the whatever we discussed, this is the equations. So you have the y, and hk, we are taking the submatrix here off, and this is, this indicates, it's a modulo n operation. So if we are talking about the estimation at the symbol here, we are talking about a matrix around that, taken to the top. So this is how it will look like. So yk is the xk times column vector plus this term hk times this is the ICA term, and this is the residual, the new noise, hk times the residual value, the difference plus the noise. So this is the ICI that we are removing, and you have a new noise. And we didn't do this. So these, you can hard slice them into back to the transmit constellation and do a ICA removal like this. But then the issue is, during the initial iterations when things are not converged very well, you introduce error propagation, which is the classic DFT issue. So we didn't do that. Whereas with the soft information, now that problem is a lot lesser. So that is essentially the idea about the interference cancellation. So cancel the interference in such a manner that you take care of you take full advantage of the Doppler diversity. Now with those y's, how do we compute the log likelihood ratios? And this is an example for a QPSK case. We assume these YKs are Gaussian distributed because the noise is Gaussian and the new noise is also assumed to be Gaussian. So that's why these expressions, this e power, these values, this is the probability of the bit being 0 and to the probability of bit being 1 for this particular constellation. And if you look at this expression, this is very simple to compute. This is a matrix, this is a column vector with 4L plus 1 elements times HK. So we are talking about a few multiplications to get the, so you remove the interference and whatever is coming, you compute these values, you get straight LLRs. So there is no matrix inversion or estimation, making an estimate of the symbol, nothing is involved. So you get the received observation vector and you do you take care of the interference in a certain manner, and whatever is coming out, you compute the LLRs with a very simple formula. This is the case of a QPSK, and similar things can be worked out for higher constellations as well. But the main point is this is a very simple expression, and with that you compute the LLRs and interleave them to get the LLRs required for the DCJR. So we looked at these two. Now we are looking at the soft mapper. This is a classic. It's being, the question here is, using these LLRs, how do you compute the conditional mean variance? And given the observation vector. So it can be worked out to be this.
So has this been used elsewhere, this particular formulation?
Yes. This is it's been taken from the existing literature.
Yeah, I thought that's pretty popular. So this is our scheme. Now the question is, how do we want to compare our scheme with a couple of others and see how it fares, and both in terms of the complexity and the performance. So we consider these two schemes that are based on MMSE estimation. And the schemes that we are going to see soon are MMSE based, and both of them takes advantage of it's very similar to what we are doing. So we took them for comparison purposes. Both of them, the schemes that we are going to see, takes advantage of the sparseness and the MMSE, and they do the MMSE estimation. Just a primer on MMSE estimator.
before we get into those schemes. Estimate is the conditional mean plus variance times the kth row of H, that is ik this, times the covariance of the observation vector inverse times the observation vector minus the mean of that standard expression. And so here, this is a matrix, and we need to invert this matrix, and that is where the complexity. We'll be talking about the O and Q and all that stuff. So this matrix could be as high if you consider the whole n. Then we are talking about an NQ matrix inversion that has, which is n by n, which is pretty big. Whereas when we talk about the submatrix, the green one that we saw before, then we are talking about a slightly smaller matrix, but still there is a matrix inversion involved. And that adds to the complexity. That's the main reason for the complexity. So this is a scheme. One of the schemes that we are going to use, the MMSE based, I call them a bit of a, it doesn't reveal much, but what does it mean? It means it is MMSE based turbo iterative, and it has got square complexity. It has got linear complexity, but square in this length. That's what it means. And so what it does is, this is a scheme that was proposed from her advisor's group. So estimation is conditional mean, the standard formula that we saw before. But they take the novelty of this idea was that it was introduced in 2005 or 6. So they make use of this matrix. And so this is how they do it.
What does OND stand for?
D is
The OND.
D. This is the 4L plus 1 is D is this 2L plus 1 is D.
It's D squared.
D squared. Yeah, D2 D squared. Yes.
That's just reflect the
Order ND, so OND2 is order ND squared.
That's
yeah, complexity.
This is the new routine we gotta learn.
Yeah. It doesn't actually, it's not defined in the thesis. Maybe it's in the list of acronyms. I don't know. I'm searching for it.
We had long discussions about whether to use something descriptive or to use some acronyms, and I'm really, I don't like acronyms very much.
Yeah.
Your son doesn't like them very much. You're supervising a lot of acronyms here.
I remember when I started doing communications, my biggest problem was the acronyms. Started reading all these papers with, 3-letter words, 4 or 5 sometimes, being ridiculous.
Yeah, I just think I defined it. I just
This is
started
the
calling
most
it.
ridiculous. O and D2. Order. Okay, fine.
I'm just saying, I don't know if it's in the list.
But yeah, it's in your list of abbreviations.
Another thing,
Those nothing.
I don't think it's there because I just named it. And there's no.
Did you name it or is it?
No, they don't have a proper name for it, so I named it. So.
You're allowed to do that, but you have to define it to your own list.
Or if you name. So you didn't invent this OND2 notation, you or Bill or. All right. Someday you're going to talk and be like, oh, that was my idea, but this isn't my,
Is it trademark? We don't even know.
No. All right, let's keep going.
Okay, so the other scheme that again it's my name. I named it, so I'll take it off.
So what is BLK2 then?
It's a block equalizer stuff. They do the matrix inversion in a single go, so they call it block. So they have something called a block equalization scheme. The idea behind it, let's explain the idea, then we'll come back. Come to that.
It's just like block squared.
So we have this matrix, this sparse matrix again, and now the idea is how do we invert this without much of complexity? So what they found is for computation of the mean and variance, you need to compute this quantity, and we know that these guys are sparse. You have 4 or 5 elements in each row or column. So when we do the inverse, you don't need to actually find the inverse of the whole matrix. Instead, the required 3 or 4 elements. So using some techniques, they come out with an inverse scheme that is just linear in complexity. It won't give you the full matrix inversion, but instead it will give you the required values of the inverse. They do it at the beginning of the iteration. They do it in a single go, and they call it block operation, and that is by that block. And the two come from, they are proposing 3 different schemes, out of which 2 is the best performer. So I call the block 2, and T for turbo equalization. For lack of a better name.
I thought it was when you fell labs T squared. But go ahead.
So their algorithm are standard matrix inversion techniques. They just pull selected data out of this matrix, or they develop a new matrix inversion method.
Yeah, they use some LDL inverse techniques and just pull the required numbers.
So they do surgically movement of the data into this canned algorithm. All right.
And with that, when you do that family, the complexity is a lot lower. I mean, you don't need to do the entire thing.
Did they talk about the accuracies involved with taking on a small set of the data?
Not really. They don't talk about that. But when we look at the results, we see that they don't lose much.
Well, compared to how much? Okay. Well,
Yeah. Compared to the other 2 schemes, yes. Okay. Now coming back to the interleave. Okay. So that is the scheme, and we know now the other competing schemes. The idea is to compare the results with the R scheme with the other 2 schemes. Now this is the simulation setup. Again, FFT size is 256. We just took that, and the number of resolvable multipath components is 30, and the cyclic prefix length is 64. And we talk about QPSK modulation and convolution encoder with this polynomial. And okay, now the randomness of the interleavers. They call it the S random interleaver, S being the 22 and 5. What that means is, before the interleaver, I mean, at the input of the interleaver, say there are 2 symbols, say A and B, and after the interleaving, there will be at least you won't find the adjacent symbols. You will be finding them at least 22 symbols away from each other. I don't know whether I'm clear there. Now you have 2 adjacent symbols, and when you interleave them, you get another sequence. In that sequence, if you look for these 2 symbols, they will be at least 22 or 5 symbols away. So the higher that number, they will be further apart. This is the case for all of them.
Are they square?
Sorry?
Are they square?
And it's just a square. You're talking about.
Interleavers?
Huh?
Are they block interleavers?
They are no. They are just random interleavers. Purely, I mean, they take it out of. No, they have some means of designing it. The way I did that was just throw. I mean, by repeated trial and error. But there are some efficient ways of designing it. But basically, it's just a random. It's not from a matrix. Not right into the serial and read back in the.
It's not that.
No.
But they assure that certain minimal distances then between these.
That's right. This is. And the way I did that was by brute force. I mean,
So the quick question, does that introduce some kind of delay or coding?
Definitely they do. They do. And that's one of the issues of turbo equalization. So with this, higher this S, higher the delay we have. And once you have a higher delay, you have more randomness in the data, but by the time you get all these things out, when your application is really delay sensitive, you cannot go for such interleavers. That is one of the.
So is the delay linear in S then? The larger S, the larger the delay?
Yeah, larger the S, larger the block length would be. I don't know whether it is linear, but larger the S, larger the symbol, the block length would be. And larger the block length, you have to wait until the whole thing comes out, right? So that is one of the issues with the turbo equalization. Complexity is one aspect of it, and the delay is the other aspect. We are just making a brief mention at the end. And so we cannot. That is one of the challenges for 802.11, for example. You have to come up with a modified scheme. It cannot tolerate this kind of a delay. The last bit in the there's a certain specification in the standards as to when how much delay it can tolerate, and if you introduce such interlevers, it cannot tolerate that. Then we have to come up with slightly different. There are schemes. You can devise again from their group, from her research group. They have come out with some schemes whereby they do not have delay, and that is by not introducing the coding in the path. Instead, whatever is coming out from the equalizer, they take the LLR and get the mean value and variance. But what will happen when you do that is you don't take advantage of the coding gains and performance suffers. And now what? And then there is some research that was done how we can optimize the interlever so that you can have a balance of the interlever length and the the randomness. And you need that randomness because you need the LLRs between the iterations to be independent. So if you can strike a good balance with the delay, the interlever, if you can design a very good interlever with minimal delay and sufficient independence, that'll be a great thing.
But that's one of the issues with design over the years. People have had these different, almost nonlinear components in this overall scheme. To do a good design has been the challenge. The holy grail is to find a design method, aside from just doing trial and error across all parameters. Right. So have we made any progress here?
Not to my knowledge.
Not to your knowledge. That's kind of the unfortunate thing that I've learned is true. Right. Okay.
Yeah. I agree with you. I mean, the biggest drawback with the turbo equalization scheme is the delay in the whole games.
Okay.
And that is one thing I will have to answer when I talk about it for a practical implementation.
Okay. But you don't have results which show the trade-off on the delay.
No. You mean lesser, smaller interlevers? Yeah, I haven't done that. That's something we'll have to, if we want to further continue on this. The interlever is something we'll have to tackle properly. Not including the coder, the decoder is not the real solution because then you're losing on the coding gain. I mean, you're missing out the coding gain part of the code. So if you do that, so that was the setup for all the schemes. I mean, all the three schemes. So when we look at the results, so we are looking at the results for iteration for one iteration, three iterations. The first iteration and third iteration. So if you look at the first iteration, this is our scheme, and this is the results of the other two schemes. Red one is one of them. So they are very close, and we are much laggy for the first iteration. But when we look at the results at the end of three iterations, and beyond three iterations, you don't get much of gain. All of us are same. So we have a higher gain across iterations compared to that. So if we stop at the first iteration, yes, our scheme is inferior. Whereas if we do three iterations, then we are now talking about equal gains. Yes. So this, to answer your question earlier, the matrix inversion. So the Snyder scheme, which is this, is using the proper. They use the standard matrix inversion technique, and these guys, block 2 guys, use their own matrix inversion schemes, and both of them have the same performance. So their inversion is not losing a lot, I would say. And now to answer the diversity thing, whatever diversity we have, we are getting even with. I mean, you do not have a matrix inversion here with our scheme, but we are leveraging on the diversity, and still you get more or less the same thing.
But if I'm interested in speed, I want to go one iteration. Why would I choose your algorithm?
If it is one iteration, no, I wouldn't use my algorithm. I mean, okay, well, we are going to see the complexity in a second. Then there is once we look at the complexity, we'll address that.
That's what I want to know. Right.
Yeah, here is, I haven't given the detailed expressions of the complexity in the slides, but certainly thesis. Now, this is the SIC map, as we call successive interference cancellation map decoding is our technique. And say we call that as 1 unit of complexity. Then this Snyder scheme has 4.5 times is 4.5 times more complex, whereas the block 2 thing is not as complex, 3.3 times.
So everybody's like 300 or more percent
Yes.
more complex
Right.
than you. But you know what? This is the day and age of cheap computation. Why do I care?
Well, there is a reason. And I'll come to that. I'll address all those questions. And this, if we talk about just the plain non-iterative scheme, the standard MMS equalization, even that is 3 times as complex as this. Now,
This is per iteration, right?
this is per iteration.
Do they scale linearly with iteration?
When the L, linear, as long as L is constant, then everything is linear. I mean, if you do 3 iterations, I mean, it will be 3 times this. But if L is high, the complexity, these numbers will scale up much higher. For other schemes, not for the, I mean, so if L is 2 at plane speeds, for one SIC map will maybe equal to 6, this number could be 5 or 6, and this will be, because your matrix inversion is cubic complexity or square complexity, and the matrix is becoming bigger, so these numbers will be scaling up much higher.
So remind me what L is?
L is it's a measure of the Doppler spread.
So this is for one iteration.
That's right. Yeah. Now let's answer the questions that you posed. One is when the silicon is so cheap, why do you care about all this multiplications? Not always. And there are 2 scenarios. One is when we talk about mobile applications. Say, for example, this 802.11 receiver or transmitter, when you both transmitter and receiver in a laptop or in a mobile phone or whatever. Say, I know in our group we are doing all sorts of gimmicks to bring down the power consumption. The silicon area, the cost may not be all that an issue, but when you have higher silicon, bigger silicon, you need to power it up always. So when you do that, you are losing the battery, and battery power is constant. So when in a mobile application, you cannot do that for that. So that is more than the cost. It is the power consumption that is causing troubles in the mobile applications. So for example, when we in the 802.11 transmitters or even receivers, they do all sorts of gimmicks. They try to power it off, put it in a standby mode, and bring down the power islands to a different voltage, 1.8, whereas the rest of things being 3.3 volts, and do all sorts of gimmicks in the silicon to bring down the power. So when we have lesser power, that is one thing. The second thing is, see, this guy is more scalable. So if you want to do one iteration of this, you need more power. You need roughly 4.5 times more power than this. So for example, if you have a cell phone and then if you're kind of dying, if your power is not good enough, then you can stop, and if you use this algorithm, you can stop it after 1 or 2 iterations. Whereas if you do that, you would have been consuming much more power, even for a single iteration. Am I clear there?
Well, on the first iteration, your performance wasn't as good, but that's still doable compared to not completing the.
Precisely.
I think I understand.
Okay, can you go back to the previous slide? Now, looking at this slide, if we ask the question, which among these cases is the least computationally expensive, that's one question. And then the one that requires the smallest amount of power.
Which is and what is the
Two questions. The one that, which one is the most computationally efficient? Which case?
Or for each iteration, the first one.
If you count the total number of, to get the results, you have the lower right corner there.
Right.
How many, which case is the most efficient computation?
Our case, the map, the SIC map, is the most efficient, and that would be like we have 3 iterations. Per iteration, you are having a savings compared to per iteration. You have a gain of, say, for example, if you compare with this scheme, we have for 1 unit of computation there, you need to do 4.5 times 4.5 units of computation per iteration, and now we are talking about 3 times. So,
but they don't do 3 iterations.
Yeah, they do.
But they don't.
They do. For the SISO case, they do. Yeah. Right. So that's what. So that is block 1. Block 3. The case is a little different for the MIMO, and we will be seeing the results later on.
I didn't see the IP part.
Right. And for the MIMO, what you said is true. For the MIMO, 3 iterations of ours will be equal. Let me not jump the guns. we'll get to that.
In terms of power consumption, I mean, if you were to implement.
If we were to implement, roughly, we can say the power scales with the complexity, I mean, almost equal to the, say, like I would, as a first level of approximation, I would say, if you need 1 unit of power, you need 4.5 units of power for that scheme because of the complexity. But it could be varied up or down a little bit. But
How do you evaluate the complexity? By computing multiplications?
That's correct. Okay, well, now talking about that, we have 4 operations: multiplications, subtractions, divisions, and additions. I didn't, the adders are, I would say, if we are talking about an 11-bit adder, which is 11 to 12-bit adder, that is at least 22 times more complex for the same speed of operation. Okay, everything scales with the speed of operation. If you are talking about very fast addition adders, we have to have carry look ahead or this, then you need more silicon area. Now, roughly you can say that, and it scales up even with the number of bits that you use. Now, a multiplier, an 11-bit multiplier and an 11-bit adder, which are working more or less at the same speed, I would say 20 times more complex. The multiplier is 22 times more complex than an adder of the same bit width. So I discarded the adders and subtractors. Adders and subtractors are the same. So I didn't take them into consideration in the computational complexity in the table that I gave in the thesis. Division is actually more complex than multiplication, but in my computation, and we are not doing any divisions, whereas others were doing. I just took them, I gave them an unfair advantage there. I just took it as 1 for using as a computation. In the other schemes, they have a few divisions, whereas we do not have, I don't think, any division. But basically, I just took them to be the same, although the dividers are more complex. We'll go on.
As long as it's not 22 adders for every multiplier.
Sorry?
As long as it's not 22 adders for every
Not really. If you do a DSP implementation, I have looked at it once, then you need 16 iterations for it. If you have a 16-bit divider, you need 16 iterations, 1 per each bit. Yeah, but it's much more complex than adder than multipliers. Okay, now we will look into the next one, which is the channel estimation. So we looked at the SISO algorithm. Now the detection algorithm. Now let's look at the channel estimation. So back again to the same thing. So we have the receiver, right? We discussed these 2 guys, and the last one remaining is this. So let's look at that. So as you see, just before we go, because of this guy, the soft mapper, you get the conditional mean and variance, and we try to leverage on that. So it's an iterative channel estimation scale. Just a high-level picture. So we are going to see these blocks in detail soon. So you have this, the equalizer, so-called canceller, and you get whatever is the y, the observation vector, gets into, you do an ICA cancellation slightly differently than that we looked before. The idea here is slightly different, so we will see the details. So we do a slightly different kind of ICA cancellation, and whatever is coming from there, we do an LS estimate and compute one set of, this is a very high level picture, we need to compute 2 parameters, out of which we compute 1 parameter from this ICA cancel data, and we compute the next parameter from the earlier one, and then reconstruct the channel instantaneous channel value. And we are going to see the details of each of those blocks.
Instantaneous channel value, but isn't delay involved?
Okay, that's okay in the sense. The equalizer, when we look at the equalizer, say in the first iteration, for any scheme for that matter, let's talk about our scheme. You need, the SIC requires only the diagonal elements for the first iteration. So that can be kind of easily computed. So you need that. And then after the first iteration, you get all these guys, and you do the computation. The moment you have the values available, you plug that in. Until then, you work with the old one.
No, I think like the confusion is what is instantaneous mean.
Oh, instantaneous.
Yeah, like what you're doing here is a block. You take a block of data and you do iterations over that.
Yeah, and then you guys, no delays built in. Is this instantaneously the channel behavior? I mean, how can that be?
When he means is interleaved channel coefficient, not instantaneous. When he says like, okay, imagine you have several reference points, right? And then you can find the channel in those. But what about the ones in between?
I think the
instantaneous is a total. You have to change that in your thing. It's not a good descriptor here.
Okay. So we use a very simple model. So we use a piecewise linear for the. It's not our idea. It was published before. So what they do is at normal Doppler values up to 20% normalized Doppler, which is where L is 1. A piecewise model for the channel. Remember, the channel is varying. Now you're trying to fit a model for that and find the parameters for that. And using those parameters, you try to find the channel instantaneous. Okay, the channel tap values for each of those. Now remember H1. I mean, we had many of those. Different coefficients. So we come out with those coefficients from two parameters, the slope and the average value. And this model will be working fine up to 20% normalized Doppler. But beyond that, you need a different scheme. You need much more sophisticated scheme. If your Doppler is too high, the linear model will not work well. And they use different other techniques, and they are much more complex. But since our idea here is to work with plane speeds or maybe train speeds, and at the verge of plane speeds, we come out with the idea that which is what the case of most of the commercial applications are. We work with this model. So with this linear model, you have these. What is drawn here is 3 origin symbols. So you have the L. The average value of the L channel tap at the J minus 1 origin symbol, and here you have the average value at the present origin symbol and the next one. Now, once you have these average values, suppose you can find that somehow, then you can find the slope between them by the standard. You can find the slope, and once you know the slope and the average value, you can fit a model like this for a piecewise linear standard. So the present value is the average plus how far away it is from the center times the slope. So essentially, the channel estimation now turns out to be the computation of this and this. The slope and the average value. Now, how do we do that? The details are the cases how we get these equations. But
so it's the channel tap is complex, right?
Channel tap is no.
Channel tap
is in the past time. Yes, it is complex.
And say it again.
In the past time is complex.
So these are complex values.
They are complex values.
Correct. So he's asking, go back to the previous slide. I think. So how do you find the slope?
Hold on.
You slope a complex value.
I have a complex value as a slope. I have to refer back to, but I think I have a complex. I mean, I treat the real and imaginary independently and compute the slope for the real and imaginary value. But I'll double check on it and get back to you.
So, but some of this is kind of a model for how it varies over the course of multiple symbols.
Right.
Yeah, over time.
So do people use this model?
When your in fact, that is what is implemented. When your Doppler is on the low side, I mean, up to 20% normalized Doppler, which is kind of highway speeds and train speeds and all. Then this model works reasonably good, and that is what is shown in one of the papers in 2003, that this model works fine. The originator of this model, they came out with at what speeds it breaks down and what speeds it works, and it's up to 20% normalized, L being 1 and 20% normalized Doppler.
Okay.
There was some commercial algorithm for the DVB-H actually.
Right. Yeah.
So this is not your model.
No. And I guess it's been there. It came the 2003 paper from Stanford, I believe. It's been implemented. This algorithm has been implemented in many, in some of the receivers that I encountered in the past.
If people try the exponential decay symbol,
Sorry,
intuitively I would think that
exponential.
the dependence on time would be not linear, but exponential will I. But for small roads,
So is it just a convenient heuristic, or does it derive from some idealized physical situation that a particular configuration?
It's more like a convenient thing. But what in that paper, it's been referred in my in the thesis by Mustafi, MUSTO team. What they did is they have some realistic data, and they try to see that generally the models follow this linear model, for load Dopplers, and so they tried to fit that, and they found that this convenient model works well for reasonable for kind of load Dopplers.
have you seen other models?
Sorry?
Other possible models?
Are there? Yes, there are. I mean, people at very high Dopplers, say L getting to the realm of 2 and 3, they try to fit different functions, say Slappian functions, or they've been talking about, there are many other complicated models that you need to do at very high Dopplers. This model breaks down, and it's been referred to. There's some basis expansion model, BEMs. That's what is being used at very high Dopplers. Yeah, but then the problem over there is it's very complex to implement. So you will be implementing it only if you really need to work at those Doppler frequencies. If you have a very very complex algorithm for taking care of a train movement of this sort of trains, then it's an overkill design.
Sure.
Yeah. So you have the diagonal elements. The catch here is the diagonal elements. These are the diagonal elements are a function of only the H average, and the off-diagonal elements are a function of the slope. So the idea is somehow get you using your mean and variance and all that stuff you have, you somehow diagonalize your matrix. The modified system matrix, from the modified system matrix you can compute this H average. And once you get the H average, you know how to compute the alphas because you have two consecutive H averages and now to answer Professor Dodd's question, when you do this, there is a delay involved. And even if you have all the computing power, in order to compute alpha, you need the past and the past H. So because of that, you need to wait for some time. So channel estimate being not in the mainstream. I mean, it's a parallel. So as and when it is available, the updated channel tags are available. You pass it on to the scheme, right, to the iterative scheme. So the delay is not much of a. The lesser the delay, the better, but it's not a very critical thing. Okay, here again, this is in the context of channel equalization, channel estimation. We are now talking about diagonalizing matrix. So unlike the frequency diversity, unless the Doppler splits diversity and all that stuff. So here, what we do is you have these mean values, and you remove the the interference, the ICI, by multiplying this by these operations, and so finally you get a new system matrix like this. So this is a diagonal matrix. So in this case, you manipulate in a slightly different manner like how you did in the past, and get a diagonalized matrix. Now, so this is the equations. So as you see, this is HKK, and this is the HKD and HKK, and this is the new system where you have only diagonal elements. And so this is the LF estimation. So Hx, so instead of x, we replace the x's with the conditional mean values, and now because this is diagonal, you can just reverse the thing. And you divide off with this mu's, then you get this equation from which you can compute the LS estimate. And this is a constant. These are our constant values. So essentially, you will be multiplying. You will be doing a filtering operation on your modified y's, which are which you obtain after one division, and you get the H averages. This can be computed and stored. Storage doesn't require power much. So it's just you have these coefficients, you multiply that with the modified observation vector, and you get the H average value.
So this works over several RGM symbols too, so that you can compute the alphas.
Yeah, you need consecutive two RGM symbols to compute the alpha for the. So there is a delay.
But your BCTR works over also a few RGM symbols.
Correct.
So do you work on this set of RGM symbols, spit out the results, and then keep your H for the next future channel estimation, or you just work on the whole block?
I say in our simulations, we have around 10 or 20 RPM symbols constitutes a packet, and that goes into the BCGR. So you have 20 RPM symbols, so you compute the H averages for all these 19 ones, and so you compute the slope for each of them, and yeah, that's how it works. And for the last RPM symbol, we just approximate the current one to the next one, and we refine the next when the new block comes. So at the edges, you have at the edges, at the last, when you have the beginning and the end. At the end, you are doing a rather a crude approximation, because the next one is not available. But that works fine because that gets interleaved all along, and with the interleaver, all that whatever you lose will be gained because of the interleaving. So that is the channel estimator. So here is the summary. You compute so these are the two parameters, and you get the diagonalized matrix, and you compute the LS estimate using it, and from that you get the H average and alphas, and stop iterations after sections are from the things. Now the results. We haven't used all the three schemes. Instead, I've compared our scheme with Snyder's scheme. I use the same channel estimation scheme that we just discussed now for both the iterative schemes that we discussed, the OND2 scheme and our scheme. And here are the results. So these two schemes. So here you have how many 30 resolvable multipath components, and Doppler is around 0.2, which is kind of the maximum for this. It's kind of an extreme case for this kind of a linear model. And we are looking at the results after 3 iterations. So the iterative schemes work more or less the same, and the non-iterative scheme, the MMSE-based non-iterative scheme, is far worse because for the iterative schemes, after the first iteration, you get the mu's for all the symbols. So it's as if this guy works with only pilot data. So you have only a few. Whereas these iterative schemes, after the first iteration, you have all the symbol mean values to aid your estimation. and this result is even more worse. Here, what happens is, suppose the number of channel taps are more than the number of pilots. In that case, you have an underdetermined system for the MMSC case, whereas that won't happen for this, because after the first iteration you have now all the new symbol mean values as working as pilots, virtual pilots. Now what is interesting is at these points, at the low SNR region, these schemes perform worse than the MMSC schemes. And that is because of the lesser convergence of these iterative schemes at low SNRs. And we will be seeing a bit more of those details subsequently.
Because you only introduce confusion, right?
Say that again?
You introduce only confusion. But your SICs are so bad that they just mess up your results, right?
Exactly right.
These results are for error probability. I know in a practical system, if I'm a user, I only care about performance and error probability. If you're doing channel estimation, you have a simulation test bed already. Are you able to, or have you even looked at taking a stored record of your channel behavior under these simulated conditions, take a look at your channel estimation result, and compare the channel estimates versus the actual channel behavior in the simulation run?
I haven't.
The proof of the pudding of the channel estimate would be really more proven there than in the BER wrapped up in some larger fashion.
But
I mean, they're kind of correlate, but it's not quite the estimation problem.
Right. So what you're saying is, look at the access channel value and look at the estimated value and see how the error goes down.
Some kind of a tightness measure, and square error, some kind of a thing. So, but I didn't see that in the thesis. I don't think.
I haven't done that.
Okay. All right.
Now, we just talk about extend the same scheme to MIMO, where we have one more interface to worry about, that is the coordinate interference. So, quickly, the generic MIMO system, you have all these symbols coming in and getting onto NT spatial streams, and they get transmitted across NT transmit antennas, and you have a channel that is kind of a matrix, and that gets back, and now you do the reverse operations as we saw before. Now, we just quickly explain our scheme for the MIMO case. So here is the the structure is exactly similar to what we saw for SISO, but what is important here is these are not elements; these are all matrices. Each of this block is a matrix, and the matrix structure looks like this. The NT transmit. This is the NT. Yes, it looks like this. So when we do the ICA removal, what we do is we compute the ICA from these guys, from the ICI that is introduced due to these block elements. Each block element corresponds to different antennas, and you do that, and that is what is done in the ICA removal, and then you get this kind of an equation. Now, what is remaining in that modified Y tilde is the coantenna interference, and there what you do is, exactly like how we did before, these we remove the interference from these guys using the same mean value. So it's a two-stage process. So you do that and get the new system. And now it's again back to the diversity and all that stuff. So we use the same schemes extended to MIMO for comparison. More results are there in the thesis, but here I just show only one case with a fairly high Doppler, and all the three schemes work more or less same when you have high Doppler. Whereas when we work with lower Doppler case, to answer the earlier question, you have lesser diversity, and the results are there in the thesis. The performance of our scheme is not as good, but the difference is not too high. It's maybe half a dB or less. So yeah. And now the complexity. Now, okay, here's so the complexity per iteration is 1 unit of that is 4.5 and 4.3 and 3.9. But the catch here is, as you pointed out earlier, because of the coantenna interference, and we will see the level of interference in the coming slides, but because of the higher interference from the the co-antenna from the, because the co-antenna, that the magnitude of that is much higher compared to the ICI. So you need more iterations for this scheme, the R scheme, to have a similar performance like the other schemes. So that is why SIC map requires 3 iterations for the same level of convergence per iterations of the other 2 schemes. So you have to scale it by, so that is why we have only lesser gains here, 43% and 50 and 30% in the MIMO case. It's not as great as it was for the SISO, but still it is performing better. So you have to multiply this with 3. So 3 units of this is equal to 1 unit of this is equal to 1. So this is 3, 4.5, 3.9, 4.3. Am I?
Maybe it's just better to do the chart with including the effect of the number of iterations.
Okay. Okay.
It's easier to have that than to explain it again.
Okay. And again, for higher the L, these matrix inversions are are more complex, so you have more savings. Now, back to the error analysis. Back during our proposal days, okay. One of the suggestions that we had from you was, Professor Fernandez, was do the error analysis and see how it works. And so we did a little bit of experimentation on that side. And so YK, the receive signal is the sum of this term and the ICI term and the co-antenna term. I mean, the co-antenna term and the SAS. So this is the ICI, residual ICI part. This is the transient symbol, this is the mu value, so this is the residual error and times the, so you get the residual ICI here and the residual co-antenna interference here. Now we are going to see how they play out for a typical, so yeah, I think it's worthwhile spending a little bit of time on this. It's a bit crowded slide though. So our experimentation is with a 2-antenna case, and this is for the, let's finish this. We did this for the MIMO. And we are talking about a reasonably good SNR, 12 dB SNR, and 2 antenna case, and carrier frequency being that high. And what we are depicting here is the co-antenna, the residual interference due to those 2 interference at different regular velocities. So to begin with, let us talk about the co-antenna interference. So we have an AWGN of minus 12 dB compared to signal, 12 dB SNR. So at this level, and at the first iteration, you see the gamma is much higher compared to the AWGN in the system. So it's around 10, almost 20 dB higher. Whereas at the end of the first iteration, this is the story of the first iteration. At the second iteration, when you have mu's and sigmas, mu's essentially, you have, okay, all this assumes perfect channel estimation. In order to understand the effects of this detection scheme, we assume the channel to be known. So in that case, at the end of the third iteration, yes, that has come down drastically, almost 10 dBs down, still higher than the AWGN in the system here. And at the end of 6 iterations, you're getting progressively better mean and variance values, so it has gone down really drastically. This is much lower. It's around 10 dB lower than the AWGN in the system. The interference due to the co-antenna interference. So it's much lesser. Now the other question is, why is it decreasing here? As our scheme gets better and better as we have higher vehicular velocities because of the diversity gains that we discussed. So your the mean and variance estimates are getting progressively better and better. So your cancellation becomes more and more effective, and that's where this goes down. So for 3 different iterations, 3 and 6, 1, 3 and 6 iterations. Now let's look at the ICI. So at very low, at static channels this should be minus infinity, but no, because of the residual errors in the system, it's around minus 60, minus 70 dB SNR, minus 70 dB power. And so, and as you go up in speed, it gradually catches up and it goes high. And one thing that is interesting to notice, is even at the highest speeds of 500 kilometers an hour, you are still below the quantity reference system. So that is this is a big killer in a typical system, MIMO system, and it goes up. And remember, even this guy is higher than the noise in the system at very high speeds. So you have a really clumsy system at this point. Like you have a very high quantity interference and a very high ICI. Now at the end of the first iteration it comes down. 3 iterations it has gone down, but at the end of 6 iterations it has significantly gone down. So if you look at the end of 6 iterations, the AWG in the system is the most promising guy, and because of that, our earlier assumption that the total noise variance can be approximated the Gaussian is fine for a typical case. So this is as low as 20 dBs and 40 dBs below the AWG in the system. So
your CAI is always at least 10 dB above your ICI.
Right. That's right.
What is the value of L?
L here, L is changing.
The highest
L
value at equals 500.
is 2. Right. At 5 gigahertz, yes. I'm not sure. I think it is the 1 rate towards getting towards 2. No, I don't think it is 2. Right. Now,
but then all these matrices, they can work with this very, very tightly banded. There's no much spread. Bell's only 1.
right.
Still.
You mean even with high Dopplers?
Yeah, you're talking about 500 kilometers. You don't even know what the L equals to.
Yeah, I know. And that is, but it will if you go. That is because it is. We are working at 5 years. If you move to say this is at 5 gigahertz, it's. If it is 2, it's the lower 2s. I mean, I'm not sure whether it is 1 or it's getting towards 2. But if you move from 5 gigahertz to say 60 gigahertz, which is what is people are talking about, then we are talking about L being no.
Yeah, it goes way up. Maybe then your algorithm has more merit at that.
Possible.
Property.
Right.
Well, he's
gigahertz, you will not be going up.
remember, it's also the 256 FT, right?
That's right.
Yeah.
Yeah.
Most of the systems like LT is 1034, 2048.
Yeah. T2 is 32.
256 is pretty low for the current systems. I think it's about packing more carriers and more tightly.
Right.
I mean, that's something that you left vague, and you should have probably tried to study more the effect, at least analytically, like back of the envelope. What is the effect of larger N, larger TS on L and D? Because it seemes to be important for what you're doing. To motivate.
It has the motivation.
Saying clearly, like, if you show to somebody, said, well, only if I'm in Japan in a fast further plane running by Newark. You said you had problems when you were in Trumpet, right?
Yeah, we had, and that's how it started with. Our office was near Highway 95, and we were doing some, myself, Rahul and Mark were doing, we had this STTV receiver, and we were fine-tuning the thing, and when a truck goes by, you get a blip in the video. So that is how it started with. And then yeah.
So that's like 100 kilometers.
Yeah, 100, yeah. But then the thing is, if you have a burst of errors, and again, remember, it's not iterative schemes or anything, it's just simple equalizers. So because they cost and power saving. So when you have that, such a simple equalizer, and when you have these blips, which is due to high VR, and then you lose the impulse synchronization is lost because the high VR, and that's why you get a blip in the video. That's where it all started. So there is no at least in my, we haven't seen much of analytical techniques for iterative schemes, at least, and this is for the Excel chart based, which was introduced by Stephen Pendring, is one of the popular techniques for the convergence analysis. And so we went with that, and that is how most of the iterative schemes are, many of these turbo equalization schemes are compared. So we went with that. So equalizer and decoders are considered to be mutual information transformers, and the trajectory of the mutual information, this will be much more clear when we look at an example. So we plot the trajectory of the mutual information exchanges. And I'm overshooting time. So, let's skip this. This is the mathematical details thereof. When we talk about the mutual information, it's the mutual information between this and this. In the case of a decoder, and in the case of an equalizer, it is between the mutual information between this and the others. Okay, this is what is shown here is the MIMO, the mutual information. I noted later that this is wrong. This legend is not correct. I'll fix that. This is SIC-MAP. Okay, so this is the input mutual information is from 0 to 1, and we look at the output mutual information. This is the case for the Snyder scheme, and this is the case for the equalizer, the turbo technique for our scheme, and this is the mutual information for the decoder. And so this corresponds to one iteration of the detector decoder. So as you see, ours starts much lower. So the convergence in the beginning is lower, as we saw in the exit and the performance results, whereas it has a hard slope. Finally, it catches up, and we saw that in the results. Final. So it needs more iterations in the MIMO case. As you see, in this case, with one iteration you get much higher gain. We saw that in the results. Whereas it needs more iterations, but eventually you get the asymptotically both has the same results. Yes, that is mostly it. Now, so we talked about the SIC-MAP, and
on the other hand, if you combine yours with, can you think of this as like if you do? I mean, I don't know, right? But if you do ICI the way you do, but for CAI you do inversion, and if it's 2 by 2, that's an easy inversion.
right.
Would that work?
It can be tried. It can be tried, and a combination of both of them.
For 2 by 2, it's
you
closed form.
Right. It is. I mean, from a bigger matrix, you bring down the matrix size by removing the ICI, and for the 2 by 2 matrix, you say, for example, you do the real matrix inversion. It's that can be tried out. So that you may have lesser number of iterations, because chi is it's possible. I mean, it's worth a try. Yes, so we saw this. That is. And what probably we can do further? A complete receiver, as we saw, we have estimation and equalization. We need the synchronization, and having seen many articles on synchronization, leveraging on the coding on the mean and variance, something that can be tried out so that we can have a complete receiver, which is what probably I will be doing as part of making it a complete receiver for. And the delimitation, we discussed this. And exit chart can be modified. The problem with the exit charts as we went along is that, especially for MIMO systems, you cannot, especially in the Doppler channels, we have a lot of what do you call it? Deep fading, and so because of that, you have you need the DER on one axis, and you need the outage probability on the other axis, and so it should be a 3-axis kind of thing. So when we talk only about the BER, the problem with BER alone analysis, what we have been doing, in my opinion, is, especially for MIMO cases, we do not worry about the outage. So it's kind of fit for AWG kind of scenario, not for a fading channel case. So so all this BR analysis is good, but we need to show the outage probability along with this. That is not shown anywhere, and at least to the extent I have done the research. So we can modify this. So in my opinion, BR doesn't make sense. Instead, BR with this outage probability is what it should be, and that so that need to be captured in the Excel charts. That is not done, and I felt that problem really because if I did not do a very long averaging, these curves won't look as it is. And by doing a very long averaging, it's as if you are kind of making it like an area division kind of scenario.
The question is, what is big here? I mean, because for you it's contradictory. I mean, you're claiming that the car is going very fast, so the channel changes fast. So, if you go over whatever 22 OFDM symbols, that you should have enough ergodicity there to get an averaging out of it. You really tackle fast fading.
Right. Right, but
the question is, like, you did go to 22 OFDM symbols, right?
Right.
That's a lot for fast fading.
Right.
So there's no, like, a concept of outage is more for very slow fading, where the blocks are slower. I mean, it comes back to your delay question and the reduced coding gain, of course.
Right, but
coding, like if you have more carriers and you have more OFDM symbols, you can have just like one or two blocks with the large codes. But anyway, these are things we can discuss later because I think we have the time now, so we can do it offline. Any more questions?